Okay. Hello, everybody. Good morning. Hope all of you are fine and doing well. So, first of all, before starting the course, I'm still evaluating your midterm exam. Hopefully, before next week, you will see the results on the Moodle. So, do you have any question about last week's lessons or any topic about the course before starting? All right, good. Today, we are going to talk about one of the most popular algorithms in machine learning. We will talk about SVM, support vector machines. We will see how we can use it in different applications, and we will understand the main concepts, and we will see what kind of different methods we can have with support vector machine. So, if we want to have a look at the outline in general perspective, we will define support vector machine at the beginning, the concepts that we need, the important elements that we need. Then we talk about the support vector classification, SVC, as a class of SVM algorithms, because we still are talking about classification and we want to focus on see how we can classify data that we have. We have linear SVC, linear support vector classification. We have class of nonlinear algorithms that they are using different kinds of kernels. I will introduce what is the kernel and how we can use it, how we can merge it with linear SVC. So for example, we have polynomial kernel for SVC, we have RBF kernel, and we have Sigmoid kernel, different kinds of mathematical equations to bring it into a cost function in order to solve problems. Meanwhile, we will define the Hinge loss as one of the most important loss that we can use it in support vector machine. As I mentioned, in order to understand these concepts, we will discuss about kernel function, and we also introduce Kernel Trick and how this Kernel Trick can work based on the kernel function to improve the performance and make it realistic to work SVM algorithms. So after finishing this chapter, you're supposed to understand how SVM is working and how we can use it in different applications in real life as one of the popular algorithms of machine learning. So let's start with defining support vector machine. We say it is widely used and it is supervised learning technique. It means that we basically assume that we have labeled data over here. We can use it for either classification and regression tasks. Mostly our focus for today is using on classification tasks, but I will explain to you later on how we can change some stuff in order to be able to use it in regression tasks. What was the regression task? We wanted to predict in the time. But classification, we wanted to classify our data. So it is supervised learning, as I mentioned, and generally with SVM, we want to find an optimal hyperplane. I will explain what is the hyperplane soon in separate slide, but if you want to understand it briefly, it is decision boundary. So what is the main objective with SVM? The main objective with support vector machines is to find the best hyperplane or the maximizing the margins between different classes. Again, we will see what is the margin definition, and we will see how we can use it to kind of move the hyperplane in order to classify our data, and visually you will see. We have definition of margin. We will soon get into it. But if you want to have a look at this figure, you can see that, let's say we have one-dimensional data. And this is the data, for example, for email as spam or ham. And if we consider only one feature, we can plot our data in this form, so that this is like x1, feature 1, whatever it is, like number of, for example, one character in the email. Then based on this number of one characters in the email, we can say that the left side are, for example, ham, and right sides are spam. Now, when we want to solve classification tasks, what we want to do, we want to kind of find a point that splits these two data to two separate parts, so that if new data comes, I can tell if it's spam or if it's ham. So I want to find this classification or split point over there. Now, if new data comes, for example here, if let's say this is our split line, so if we have a look, it's completely separating data to the left side and right side, and in the right side, if we call this decision boundary shows that right side are spam, left side are ham, and no problem. But the point is, now if new data comes, and if new data is over there, so it means that our feature 1, x1, says number of $ character in email is like this amount, and it's over here. Or this point that splitted our class to the left and right, so says that this new data that is coming is belonging to left, that is ham. But the point is, if we have a look, it should not be really belonging to the left, because generally as human we can see that it is closer to the right side, to the spam one. So it's supposed to be more likely spam rather than being ham. And this is the problem. If we split our data based on the one point that is over here, it is kind of, although splitting the data, classifying our data, but it is not very good classification or decision boundary. So what is better idea that SVM says? SVM says, okay, instead of like using different techniques, for example, we've seen some models already that doing this for us, we can say, instead use some margin to find midpoint, so that this decision boundary, instead of being here, we can push it somewhere to middle. So the whole idea in SVM is to find the margins, the edge data, so that after finding this edge data, we can push the line somewhere in middle, so that we assume that we have better classification for our problem. Is it clear for everybody? So based on these margins, we want to, instead of having decision boundary somewhere else, we want to try to push it in center. In one-dimensional, this is quite visible. Now let's say, okay, what is the support SVM? We say it is specific instance of the, what is the SVC? Excuse me. So support vector classification, we say it is a specific instance of the SVM algorithms that we want to specifically use for classification tasks. And there are different SVC algorithms that includes in this SVM. If you want to have a general look of the what we have in SVM, we can say we have support vector machine. Under that, we have support vector classification algorithms. As I mentioned in the outline that we are going to study today, we have linear SVC, we have nonlinear SVC, that is including polynomial kernel, RBF Kernel SVC, Sigmoid Kernel. These are all under class of the SVC, support vector classification. On the other hand, we have problems of the support vector regression, that here, instead of classification, we want to solve regression problems. Again, we have linear SVR this time. We call it, instead of SVC, we call it SVR. We have nonlinear SVR. That nonlinear SVR again can be with the kernel of the RBF kernel. We can have it with polynomial kernel, and we can have it with Sigmoid kernel. These are the most traditional SVM problems. But what about the most advanced ones that we can study and see is least square SVM, LS SVM. That again, it has two categories. We can use it for classification. We can use it for regression. On the other hand, we also have twin support vector machine, TWSVM, that again can be for classification and regression. And these two models over here are kind of more advanced versions of the SVM algorithms. But what we are going to study today, of course, in machine learning, we have hundreds of thousands of different techniques. We cannot cover all in this class. We will see the most important part. We will see the SVC, that including linear and nonlinear models, so that if you want to use it to regression, I will explain to you also how you do that, and also some tricks, some changes in them can lead us to have more advanced models that later you can have a look and study. So now let's start with key concepts in support vector machine. Before starting to understand it, we need to know, for example, what is the hyperplane, what is the margin, what is the support vectors, what are the support vectors, what is the regularization, and what is the kernel trick. So we one by one specify these. Then meanwhile that we are talking about kernel trick and regularization, we will explain also the SVC algorithm that is for classification in support vector machine techniques. So first of all, let's start with hyperplane. It's very simple to understand. We say it's a feature space that has one dimension less than number of the features that we have, and it's also called as decision boundary. So always the number of features that you have, your hyperplane has one lower dimension. So that in one-dimensional space, we have a point. In two-dimensional, to split the data, you saw example. In two-dimensional space, we have a line. In three-dimensional space, we have 2D surface, two-dimensional surface. And with more than four-dimensional spaces that we cannot actually plot it sometimes if it's too big, we have hyperplane. So these are different definitions that you can use depending on the dimension of data that you have, but most of the time we can call them as hyperplane. For all the cases, still we can call them as hyperplane, but it's like formally for more than 4 dimensions. Other ones we can call it the other parts. So the same point over here I stated for you. Now if you want to visually see what is it looking like, so if your feature space is looking like this, the data, then we have a point to split the data. On the other hand, if you have 2 dimension over here, we have a line that is of course 1 dimension less and 1-dimensional line to split the data. And if you have 3D data over here that you can see, we can have a plane or hyperplane or a surface to split our data into 2 classes, for example, if it's binary classification. So you can see this data is for tumor, that kind of disease for tumor size tumor location and patient age. That can be malignant or benign. That is two classes formally that showing that it is safe or unsafe for body. So what we want to do with SVM, we want to work with this hyperplane. We want to see how we can define best hyperplane for our data in different dimensions. We don't care what will be the dimension. Now let's define second term that we are going to use in support vector machines. It is support vectors. So what are the support vectors? Are the data that are closest to the hyperplane that we have. So these closest data, we use it also to define the margin. Okay, what happened? So we want to define some closest point to the hyperplane, then use them to also define next term that we have as margin, we will see. So it is critical to determine optimal hyperplane when we want to define them. Let's say visually quickly see what's happening. We have some data. These data are labeled. So these colors are showing labels of the data. Let's say whatever the example we have this class A, this class B, and we want to find the hyperplane in order to split them so that if new data comes based on the X and Y, we can say which class it is belonging to. This hyperplane is split like for example, if new data comes in this point, we want to say in class orange. Or it is here, we want to say it is in class blue. Now, what are the support vectors? Support vectors are these data that are the closest to these lines that we have. And these lines are margins. So we have a hyperplane, and we have margin lines, and support vectors are the closest points to those lines over there. Actually, we want to use those closest points in order to find the best hyperplane, and based on that define the actually we define the margins, then we define the hyperplane based on that margin. So I define the margin now. Now it should be very simple. The distances between the closest points of different classes to the hyperplane. In SVM, we try to maximize the margin to push it to the border that fits into the data. So if we want to maximize the margin, those two lines, we call the technique called maximum margin classifier. Later we're going to change this because it has some issues, we will see. But when we want to push the margins to the edge of the first data that we see from each class, we call it maximum margin classifier. So maximum margin classifier has some objectives, two objectives. One is the classification performance, to improve the classification performance. Second is generalization of the model that we have, so that if new data comes, new sample data comes, still it can work perfectly fine. The definition of generalization. So visually you can see the margin over there. These are the data. And the distances between the edge support vectors, so we call them as support vectors, to the hyperplane that we have, this area called margin. And what does maximum margin classifier is trying to do? Is trying to push it to the point that is as close as possible to support vectors, so that we have bigger space over there, so that this hyperplane is in center and makes sense that new data comes somewhere nearby here. It is more likely to belonging to the, for example, orange class. Any question? Is it clear? Okay, good. So we say, okay, now with maximum margin classifier, the hyperplane may get very close to one class. Think how that can be possible. Any idea from you guys how it can be possible? Because in maximum margin classifier, we say that, okay, we have hyperplane, we want to push the lines to the support vectors. Now we state a problem. We say we may get too close to one of the classes. How? If anybody says, get positive mark. It's very simple. Simon wants to answer. Okay, let's see. We say the maximum margin classifier is super sensitive to outlier data. And what is the outlier data? Outlier data is, where are the markers? Here. So we have some data. What we call as outlier data. Suddenly one data is here, one data is here, one data is here. But thousands of data are there. Those are called outlier data, some kind of noise, some kind of mismeasurement, or something like as exception. These are called outlier data, very popular to use in image processing, machine vision. In many algorithms we have this, and we should kind of find a way to filter these over there. So that we say the maximum margin classifier is super sensitive to outlier data. Now you can find the answer. Why? Because those margins can be pushed with these data, right? Instead of being here, can be pushed over there. So that let's look how it's looked, how maybe can happen. We have a class, we have a data with two classes, it's clear. And let's say we can define the margin and we can define the hyperplane so far. No problem. Now the issue is, okay, if there is another data over here instead of that one, that this data is over here. Now, how the hyperplane and how the margins are looking like? They will look like this instead, with maximum margin classifier. Because we have the hyperplane, split it into two, and the algorithm pushes this margin to the edges of the classes that we have. And so far, we may say, okay, that's not issue. It's working pretty fine. It can classify to the two classes. Accuracy is like 100% here. But the issue comes when you have a data over here. So we have a sample data that comes over there. Now, if you look at the data, this looks like should be the blue class, right? Because it's more close to all these blues over there. But our maximum margin classifier says that this is orange class because it's like in the left side of this hyperplane. And we can say this is wrong class. Now what do you think we can do to solve this problem? Any idea from you guys? Let's say you are engineer at the point that they invented a maximum margin classifier and you want to improve it. So what you think you can do? Yeah? Can be, but that's like eating the bread instead of here from there, make it more difficult. Because detecting outlier is not easy, right? Because you need to find the class center and filter the outlier. And what your friend says also is very common to be used in different advanced techniques to improve the performance. To detect the outlier, detect his noise, filter, remove these, then try to solve the problem. Okay, let's continue. So we will see how to solve this. We can release this to new algorithm instead of saying that, okay, we have limitations of the support vectors to be support vectors to that any of these margin lines cannot cross it. We can release the constraints so that we can say, okay, these margin lines can have some error. So if you release this to have some error, then this can grow. By purpose, if we allow some error over there. That's what we call it as regularization, or make it easier to solve. Because here, when accuracy is 100%, that actually somehow overfit is happening. You see, we classify data pretty accurate. When new data comes, our classification is wrong. Actually, overfit is happening over there that we want to also, at the same time, solve that problem. So we say with regularization, we want to allow some misclassifications. We need to have bias variance trade-offs. That is very similar that we have done already. We discussed it a lot. What is the bias variance trade-off? And we want to do the same here, so that it means that the model complexity and simplicity should be kind of in trade-off, so that it's not too simple, it's not too complex too. So that in order to do this, we are going to introduce a parameter, very famous parameter in SVM called parameter C. This parameter C will define how much we want to allow the regularization, or how much we want to let our model to make errors in terms of those margins. So here we say, okay, we want to do the balance as I explained, and with the term C, the values that we can indicate with C, that we will see how we can also write code and implement it later on. We say if we define higher misclassification, if we define C that higher misclassification accepted, we can have wider margin for training data, so that the margin that we are defining, if I draw it here with other color, it is going to be get bigger or wider. If we want to have higher misclassification, to do this, we should decrease the SC. If we want to do the vice versa, we need to increase the C, and then lower misclassification will be accepted. So it means that our margin is going to be narrowed down to the edges of the points, data points that we have. If I consider these data points here and the other class, over here, then my classification will look like this, because when the margin is increasing, my misclassifications numbers is increasing too. Let me also add those points over there so that you can visually imagine. So we want to add a parameter c. We will see the equations and terms, and we want to control it to control the margin over there. So for allowing misclassification by C, also here you can see visually that for the previous example, the data that was here this time instead can be allowed to misclassified by purpose. And if we do this, we can call it now soft margin. So we define soft margin, but already we know that the label of this class, because we have already the label, this data set that we know that this belonging to the orange, but by purpose, we allow to have misclassification so that we assuming this data set over here, this old data over here, supposed to be in class blue most likely, so that if new sample comes, our accuracy of prediction is much more higher then. I think you need to turn on ACs, please. Okay, thank you. Now what is happening here? If new data comes, for example, let's say this green is new data that we don't have its label. So how it will be in correct class because it's in right side, and if it's blue. If we knew that really it is blue, but we wanted to test it without giving the label, then it is correct and makes sense that whole this class, whole this data supposed to be at the same one class. Is it clear? Any question? So as I mentioned, if we allow the misclassification, we call it soft margin, and then we change the algorithm name as soft margin classifier instead of maximum margin classifier. Now we have soft margin classifier that can be used in support vector classification algorithm, or any other algorithm can be used to in class of the support vector machine. The point is, sometimes I see students doing mistake after especially explanation of the equations for calculations of the cost matrix and find that hyperplane. We will see how we do that. Is that they think that C is directly related to how many mistakes my classifier can have. Because like you may think that, okay, if I put C number 2, C equal to 5, then it means that 5 of these data can be misclassified, but not really. The C is not exactly determining how many misclassification I want to do with data. C is a metric that can kind of work in the equation in order to allow how many misclassification that we have. And we will see how we can then find the proper value for C. I will explain the whole procedure, how to find it. And you will see how useful the last courses that we've had are in this class. We are going to use them also again and a lot. It's kind of chain of the things that we are learning in order to learn more advanced techniques. So then we can say C determines the balance between margin and the classification error. So when you are increasing the margin, you are increasing the error of model, right? Because the error is increasing over there too. But that's by purpose that we want to achieve the regularization. Classification error in objective function can be defined by what we already studied, by, for example, accuracy, precision, recall, F1 score to optimize the algorithm during training that we will discuss. So similar to other classification problems that we introduced the metrics, we can use it in SVM, use all of them in SVM in order to see how accurate my model over there is, and I will be able to also train. If you want to say, okay, let's have a look how we can choose the best soft margin. If you want to answer this question, we can say we can use now cross-validation based on the metrics that we discussed, like accuracy, precision, recall, F1 score, that last lesson we studied. We can say, okay, what is the best value for C? What does it mean? It means that I can change the value for C, that each time I can allow this margin to make it bigger or smaller. My data set is existing, I make it bigger or smaller with changing the C. Then each time I'm applying the cross-validation with, for example, k-fold, 5-fold cross-validation. Then I evaluate, for example, F1 score. F1 score for this model, this margin size, give me some value, and for this one also give me some value. I can try it many times, and with cross-validation, then choose the best one. So that you see, we need to use cross-validation technique that we studied in detail. We need to use all the metrics that we studied in detail, and also we need a little bit more. We will discuss it later. We need feature selection too. So then we say, then we can change C and evaluate, allowing the misclassification to change the to choose the best soft margin that we can have. Here also I visualized for you. You can see again the data set that we have. Then you can change the soft margin and these margins. Then you can choose which one is working best with the metrics that we have. If you want to implement directly the cross-validation score, before I asked you to do it yourself, you did it as practice many times. But as you know, most of the things that we are doing are available in Python or different languages as library. And if you want to do that, it's very simple, just goes to 2 lines. Already they implemented for you. For example, from scikit-learn, you can import the cross-validation score, and after you import it, just 1 line. Scores is equal to cross-validation score. You give the classifier, you give the X as data input, Y as labels that you have, number of folds that you want to have, like, for example, cross-validation fold is equal to 5 here. It means that we have 5-fold cross-validation. And what is the scoring metric that we have? We already studied accuracy, precision, recall, F1 score. So that, for example, I put it here, accuracy for you. So exactly what we studied in last lessons are coming in 1 line here. You can give the parameters as input, then it can do cross-validation on the classifier, the model that you have, on the data that you have, X and Y, a number of folds, and the accuracy metric that you want. So for scoring, I stated here, you can give the accuracy, so you can change this to accuracy. We already have precision, recall, F1 macro, and F1 itself. F1 is for binary, F1 macro is for multi-classes. Just a little bit names are changed, but both are the same metric that we discussed already in last chapter, and also you can use it average precision inside there. So it can do whole this process in 2 lines for you. Okay. Now let's have a general view what we need to do with SVM, then go in details of how we can train the model and what are the important things in order to find that hyperplane. So we know the basics now, we know the hyperplane, we know the margin, we know the support vectors, and we know that we can use cross-validation in order to find C, to determine that margin. These are the kind of introduction that we needed to know in order to understand whole concept. Now we want to see the SVM's steps in general, then we dive into the training the model. So these basic steps of SVM that I'm going to explain also is valid for different classification techniques. So first what you need to do data preparation, so that you need to collect and organize your data that you have, whatever the problem is. It is image processing task, it is email spam detection, it is in robotics, in whatever we have. And of course, after you collect and organize your data, you need to split it to training and test set. After data preparation, you have the feature selection step. That in feature selection step, we select the features that are most important to our classification task. There is some points over here. In some cases, like some data, you don't need to do any calculation or something. You just directly can feed data to algorithm. But in some tasks, your feature should be extracted. For example, if you have image, then you may need to extract the edges. You may need to apply some pre-processing techniques in order to extract your feature from pure data. And this is actually the differences of machine learning, all machine learning techniques with deep learning. In deep learning, we usually don't do any pre-process. We give the data purely to model and train it. Later on, we will see. But in machine learning, we need to do feature selection, and we need to not only say which feature is important for us that we studied, we need to do write some code, develop something to extract those features, then later to feed it to our algorithm. For example, in face recognition, we can use SVM. It's also very common. You can see many examples to do that. But then you need to, for example, extract some features of eyes, nose, for example, nose size, lip size. You need to extract some features, then give it to SVM, then SVM works for you. And that's the kind of key differences of machine learning and deep learning techniques. And we already answered that. It's still advanced companies, in advanced deep learning, in advanced machine learning techniques, we still use traditional machine learning algorithms. It's not in every classes, in every cases, deep learning works perfectly fine. Still, these algorithms are used in big companies in order to develop advanced techniques. So then, after your feature selection step, we also discussed how you can do that in terms of choosing important features. You can apply the same things over there. We have the model training. In model training, we want to train SVM models on our training data to find the hyperplane that separates the data in base situation. This is the part that we will discuss today. We will focus upon it, how this can happen with support vector machine. On the other hand, after like model training, we have these steps of the hyperparameter tuning. So for hyperparameter tuning, in almost all machine learning techniques, we have some variables that we need to adjust some values inside. For example, you remember one, learning rate. You needed to adjust the learning rate for regression models in order to tune it. So here we will have the same. So there are some parameters that we need to tune to achieve best performance of our classification task. So this includes regularization parameters, for example, C, and some kernel parameters that we will discuss later on. What is the kernel? After hyperparameter tuning, we have model evaluation, that you know how to do that now clearly. We evaluate the performance of the model, for example, with accuracy, precision, recall, F1 score, or cross-validation itself. When we've done all of these, we can use our model. And what does it mean? It means that after you train your classifier on the test and train data set, you bring it to use, and then you can do prediction based on new samples that come and you didn't have that data. For first time your model sees and says which class is supposed to be. And if it is accurate, that's it. Then you can install it somewhere in real life application, then it works for you. For example, can you say any example? Every day you are using this. Every day, no exception. Your email for your spam detector already does this for you and sends the emails to the spam or ham. There are many other you can think now if you are using. Are there in your cell phone, for example? Of course there are. Are there in computer that you are using? Of course they are. And you can think yourself that what it can be. So we want to see how we can train support vector classifier. We basically say the concept is looking like similar to linear regression. Why? Because this hyperplane is a line, right? In this model in 2D. In 3D is hyperplane, and looks like very similar to what we were doing in regression model, right? We were in regression task, we were finding kind of intercept and slope in order to say how to split those data. The whole thing that we are going to do is pretty similar, but the technique that we are going to use is totally different in order to do that. So we say, okay, we have a couple of steps to do this. What is the first step? In first step, we say, let's first of all talk about linear models, linear support vector classifier. It means that everything that we are talking is linear to make it simpler. Later, I will extend it to nonlinear with adding some more complex kernels, we will see. But let's assume for now model is linear. And the goal is to find the best hyperparameters to separate two classes. We declared many times by, for example, maximizing the margins between them. So what we can write as equation for doing this, we can write the equation like this, that f of the x is equal to w times x added by b. This b is pretty familiar for us, is bias term. Very similar to what we've had in regression model. But here, the x's that was also our data, input data, is times to the is times by dot product to the weights vector. That each one of these features are getting a weight that defined by w vector, that we want to find kind of proper w's and bias term beta in order to solve our problem in linear one. And how it looks like, it means that we want to find the line to separate our data into two classes by finding proper w's and betas. The biases, not beta. Is it clear so far? The objective should be very clear. We want to find those lines. And the whole concept is looking like linear regression. Now, after defining the problem, what we need to do? We say we can use now, similarly to previous regression model, what we've done, we use one optimization technique like gradient descent or stochastic gradient descent, or we have many different techniques in order to fine-tune and find the parameters that we want. Okay? So in order to do this, what we were doing as one of the very important elements, we were defining the objective function. Now whole differences starts from here. In regression model, we define the objective function for example, gradient descent based on, for example, Euclidean distance, Manhattan distance, and we've written the gradient based on that, and we developed the equation. But here, we want to define it based on these margins this time. The concept of the margin in support vector machine. How we can do that? We need to write almost a big equation, but it's not too complicated as it looks like. Let's have a look. Break it by one part by one part. So here we have two side terms. The xi's are defining the feature vectors of i's training example, is like the data that we have. The y's are the labels, the true values of the labels. But here in the objective function, instead of 0, 1 or true false, we define as -1 and 1 over here. I will explain soon what is this part is doing. We want to run whole this term over here to all our learning data in the right side of the term. In the left side of the term, we already defined the C. C is to find the best margin, the size of the margin that we define. Let me also write it here. See how big margin I want to be with the value that I want to declare over here. And we have here the weights. But the weights should be in form of the Euclidean norm. Euclidean norm, or some of the squares of the elements, looks like this. You know that with some of the squares of the elements, we can write it in this form, that it indicates the sum of the or elements or weights that we have, but squares of them. So each one of the elements get squared, then we get sum, then we calculate it and we put it over there on the W. So we declared all the elements. What we want to do, we want to find proper W's, the weights, and B as bias as our last function in order to find best metrics over there. But what more we need to do, we need to know that this term over here is the distance from the ice training example on the decision boundary, determines that for me, and this maximum is to ensure that the loss is not negative, because it's maximum of the 0 in the left side and this term over here. If it's negative, we replace 0. Otherwise, we replace the value that we have on the right side. If we want to declare whole this part over here, maybe a little bit complicated, but let me break it down. We call it as Hinge loss function. This is famous in machine learning, that equation over here can be declared as Hinge loss function. It is commonly used in SVC or SVM algorithms. We use this Hinge function to extend it, and we will see how we can add some kernels into that. The Hinge objective is boost the model to find optimal separating hyperplane that at the same time also give penalties to the data points that are inside the margin. So the whole concept here is the whole concept of this equation over here, that we indicated each element. We say that, okay, when we declare that distance from i's training example to the decision boundary, it means that we want to kind of say how good this margin over here is. Meanwhile, I'm penalizing when I'm doing wrong classification that is included inside that margin. So we are not limited to this Hinge function. There are different versions of Hinge function. For example, squared Hinge loss, Huberized one, logistic loss, and exponential loss. The equation here can be changed in order to evaluate this part in different forms. So now we should say, in most cases, we don't need to use this. You may say, okay, there are many loss functions over there. Instead of Hinge, how should I know which one to use? I'm telling you that this Hinge function is very popular, and in most cases it works. And it is by default has been used in many libraries. That I will show it soon. This Hinge loss usually should be used with linear loss kernel. We will define loss kernel in order to be able to add it inside. But for now, let me define the Hinge loss. So I can, this is the same equation. I can, if I want to separate exactly the Hinge loss, I can write the Hinge loss is equal to maximum of this term 0 and 1 minus this this term over here. Y is the labels again, the labels that can be -1 or 1, label of data that is in two classes, for example here. The W weights with xi's as features that I have added by some bias. We say if a point is correctly classified, and now I want to define what does it mean. So to understand it better, what does this term over here mean as Hinge function? To based on that margins over there. We say if a point is correctly classified and is outside of the margin, what does it mean? Correctly classified, so this is my line over here, my hyperplane. So these are correctly classified because these are on the left side, and they are outside of the margin. They are outside of the margin. Let me maybe clean one of these margins to make it a little bit simpler to understand over here. Okay. Okay, correctly classified ones and outside of the margin. And maybe add some also later on. We want to use these. We need some also inside. In this case, correctly classified and outside of the margin, we can say Hinge loss is equal to 0, this term over here. We want to understand what is happening mathematically over there to make it more clear. On the other case, we say if a point is correctly classified again, but it is inside the margin, like this red dot here, or this one here, the point. Then what happens, this equation, the Hinge loss that is plugged in there, can be in this term, greater than 0, but less than, the value will be between 0 and 1, which means that it is not negative, it is positive. On the other hand, if it is misclassified, this red point completely misclassified. It's like in right side of the hyperplane over there. Then what we call it in equation, how we can show that in terms of equation, we can say hinge loss is greater or equal to 1. All the values or that indicated as greater or equal to 1 in hinge function says that, okay, all are these points. Now you can see, based on this declaration, if I get some of these definitions over here as hinge function, I can clearly state what the points are, where are they, and how should I include it into my value. Like this is wrong value, then I can go with this term over here because the value is greater than 1. Is it clear? The equation may look complicated, but if you look at these terms over here, how we can work on each one of the data, if they are inside margin, outside, or wrongly classified, then get some of them, then the equation should be simple. The definition of all that plug times C. C is to declare how margin should be big and small. You can see it's working as a scale times this. And in the left side, I visually, next slide, I will show this part too soon. That we already declared how this W is sum of the squared weights. If you have a look in this data, we can say that, okay, if we have this hyperplane and we have these two margins, this left margin over here can be written as this term. The weights times x added by bias is equal to -1. So if this term is equal to -1, it declares this margin for me. That is also known as negative hyperplane. If my term W times X, that is inner product, times bias is equal to 0, then this indicates my hyperplane. On the other hand, if we have the value equal to 1, it indicates my positive hyperplane. So what's the W? The W's are the weights. The weights that indicating how this should move over there, the hyperplane. On the other hand, the size of here can be shown as 2 over the Euclidean form of the norm of the W's. And this indicates the size between margins. In the equation, just plugged in the equation over there. Visually, if you look, it will be more understandable in that term too. Now, what we need to do, okay, we declared the equation, objective function. What we need to do, we need to converge with optimization algorithm simply. And we can then define the decision boundary. What optimization algorithm we can use? We can use same, for example, gradient descent, the stochastic gradient descent. Instead, this time we want to find the bias and W's, and those bias and W's indicating slopes and intercepts for me as we were defining in linear regression. So we can say the slope is the decision boundary, which is normalized weighted vector W, and intercept is coming from bias that we defined with the same equation over there, like this one. So it means that this W slopes indicate the slopes for me, B indicates the intercept for me. So we have a challenge that the actual support vector machine use is coming to solve this problem. So any question before that? I think maybe we can have just 5-minute break. Then we continue with the challenge and we will see how really we can apply it. And about the equation, one point about that equation that looks complicated, I will show you implementation that you will see how simple it is. Okay, just short break. Okay, attention's back. Everybody? Now is machine learning time, not the sleep time. Hello? Machine learning time, wake up. Important course. Okay, everybody awake? 100%? Let me see your faces. Okay, good. What we are doing, we are learning SVM, and with SVM, we wanted to use it for classification, and for classification, we said that we want to find one line. To class of data, we want to find one line, simply. And we said this looks like linear, this looks like regression problem, that we were finding the intercept and the slope, the slope and the bias, that we say, okay, what is the angle and what's the bias? And we want to solve almost similar problem, but we said in different way. And here what we do, we want to work with margin instead to split the data. What we've done, we said, okay, we have same concept of the cross-validation, we have same concept of the accuracy of the model that we have, and we have everything pretty similar, and we have SGD, stochastic gradient descent or gradient descent, to optimize the values that we have. The thing as it is different is objective. An objective, of course, should be defined based on this margin. And this margin definition we define in this equation. We said that we want to have a loss function or objective function, that we want to find two parameters, W's and bias, weights and bias, that these two indicates where this line should be, clearly. And how we can say where this line should be, we should kind of measure how many of these data points are classified correctly or wrongly. And we defined it in the right side of term over here, simply. We said how many are correctly classified or outside of, correctly classified and outside of this margin. How many are correctly classified and inside of margin? How many are wrong, like this point? We kind of have some metric to declare that, with some C parameter to say how big should be this margin, how this should be wide. So that then I want to find the intercept and the slope. And we said, okay, if we solve this objective function with gradient descent to find these parameters, after solving it, this W here gives me the slope, and this bias gives me the intercept. Exactly same as regression model. Then we know where is the line, simply. Clear? We didn't do very complex thing. Just simply we solve linear support vector classification problem so far. Now the question is, okay, is everything like this simple? The data are very clearly here in the left side, right side, everything linear, and you can put the line over there? Of course it is not. In some problems, we say data points are not separated, of course, linearly. So that, let's say we have a data set that looks like this. Your data for first class, mostly in left side, but some part in right side. From some small threshold are in class A, from that big threshold is also in class A, but in middle they are in class B. For one feature, one value. For example, the chance for one specific disease when you are a child and when you are very old is high. Then you want to classify this. Then how we can use that SVM now? Can you put a line or put a point over there? So if you want to put the line here or a split line over here, it's wrong. And if you put it here, it's wrong. We cannot have two. It's like just this. This indicates that if you put it here, then whole this is wrong. If you put it here, whole this. If you put it in middle, it's wrong still. It's not accurate. What we need to do, we need to kind of figure it out with support vector machine. We say in such a cases, we can use kernel function that maps the data into higher dimensional space to solve the problem. Think about it, how it's possible if we want to solve with higher dimensional space. Now I want to feel that guy who invented this approach. Somebody invented the SVM, right? So that person was thinking about this problem, this issue, then thinking, okay, how I can solve this, and imagine that if I bring it to higher dimension, I can solve it. I give you the answer. Then you imagine what he's done, what can be. No idea? Okay, if you say, I give you positive mark again. No idea? Yeah? Yeah, correct. Yeah, your friend is correct. Now let's see how we can do that. So we want to define some kernel function to increase the dimension. In the next slide we will see exactly to be able to separate this. In order to do that, we want to define some kernel functions. That these kernel functions are different, we will discuss it. They can be linear, they can be polynomial, they can be radial bias function, RBF, they can be sigmoid. These are four commonly very important kernel functions that we can use for SVM in order to solve this problem. So let's see how we can do that. The solution is, as I mentioned, we can add one more dimension. And for example, after adding one more dimension, we can add some simple equation, for example, square of the data or cubic of the data after defining the kernel that we have. So first of all, let's have a look what is happening. The same data that we have over here. Left side, right side, and middle. Now, I cannot classify this with one point because we said that our hyperplane for dimension is -1. Here, I should split it with 1 point into two classes because it's binary classification. So what I want to do, I want to add one new dimension, d equal to 2. And after adding one new dimension, now I need to choose one of the approaches, like one of the equations that I want to apply on it to bring it to higher dimension because I need second dimension in order to be able to split it. Let's say I choose the x to the power 2. So if I do that, what happens? You have this data here, some value like 2. 2 to the power of 2 becomes 4, right? The point goes up. Just 2 to the power of 2, 4, it goes there, I plot it. And I continue that with like the other point. I continue. For each one of these data, I continue that. I continue. For each one of these, I bring it to the second dimension. I continue, and you look at new data. What is happening? Now data is like looking more understandable for my model to be able to have a line to split it, or hyperplane to split it. If we run it, you can see with this green hyperplane, I'm able to split the class into 2. These are pretty fine split to class orange, and these ones pretty fine split to class blue. Is it clear? So it says that, so here we have just 2 dimensions. You may have 100 dimensions. You can increase the dimension in order to make something similar to be able to split it. But we have different kernels that they have different approaches. And for each approach, we can have different parameters and values over there. So the question is, are we limited to increase the dimension just only 1? Or we can increase it as much as we want? What do you think? Any idea? In SVM, we can increase it as much as we want. In order to achieve, because maybe you increase it, still you cannot classify it. Increase 1, you still, this line is not good still. The data separation is somehow, that is still very difficult to separate the data. Then you can increase 1 more dimension. But the question is how we can define how many dimensions we can increase or decrease. Like if we increase a lot, then decrease back. Who can say? Cross-validation again. We can apply cross-validation for each dimension, increase, decrease, in order to find best, because cross-validation gives us how good it is, right? How good this model is, my model is. I can increase dimension to see in which dimension my SVM model works perfectly fine. So now if test data comes, what should I do? For the test data, I apply the same. I bring it to new dimension. Then support vector machine, this hyperplane, says that, okay, this is an orange line because it's under the curve, under the hyperplane. And it's classified correctly. What if I apply x cubic? Then what happens? To the power of 3, then you can see that it is going like that. Can I use another function, like exponential function? Yes, you can use exponential function. You can use another function that maybe is like this. Whatever you want, you can use it there. But we want to formalize it in kernel. And if we define the kernel, then we don't need to define it over there. We don't need to choose this. Then the kernel already has the definition for us. So I answered how many dimensions you should do. You can do and try it with cross-validation. And now we want to talk about kernel functions. First of all, we define kernel function. Second, we talk about the kernel trick. Kernel function was what we've seen. Map the data into higher dimension to make it linearly separatable. We want to draw a line to separate. But on the other hand, we have definition of the kernel trick, that in kernel trick we say, instead of doing that, instead of like what we plotted there, that's costly and complicated, instead we can write some equations, that those equations, without explicitly transforming data to higher dimension, can calculate that for us. We don't want to transfer all, then do all, because if the data set is big and very complex and lots of problems because of that, if we do that and write some equations that explicitly transforms the data instead of really transforms, then we call it as kernel trick simply in SVM. So kernel trick allows the model to learn nonlinear decision boundaries efficiently with lower complexity. So another example here, you can see this data. That was one-dimensional problem. This is two-dimensional. Let's assume you have a data set like this, your data looking like this. So with support vector machine, can you draw a line to split it to two classes? Whatever you draw is wrong. There are lots of errors. But with SVM, with kernel, what we can do, we can apply kernel to bring it higher dimension, add one more dimension. The data will look like this in 3D. Then you can have hyperplane. This green is hyperplane that is split the blue ones upside and orange ones downside. Clear? In one-dimensional you saw, in two-dimensional again you can see, but if you increase the dimension, it's not visible anymore. But how we can make sure that it is working? Cross-validation, the numbers, accuracy, precision, recall will give you values. Then you can interpret your model based on that. You don't need to see. You have millions of data. Finally, you see the cross-validation value, F1 is score value, what is it, and you know how to interpret it. Then you don't care. You just apply it and choose best model for your classification problem. This classification problem again can be in image processing, like detecting cat from dog, if it's binary classification. So let's see the popular kernel functions. We have linear kernel function. For the kernel function, now let me clarify one thing for you. So for SVM, we've written objective function, right? That objective function, we're working based on linear. Then we want to add kernel to that objective function now. So not only we want to define new kernels, later on we should modify that objective function too to plug this into that objective function. So first of all, let's see how we can define kernels. Later, we modify that objective function so that we can plug these kernels as we need. So in linear kernel, we can write the kernel xi's, xj's is equal to the inner product of the xi's, xj's. What is the xi, xj? I and j represents the I is like the current dimension, the j is the other dimension that we increase this +1. So I've written also here with the linear kernel, we want to compute the inner products between two data points. If you have problems with math, of course, I've also stated some example here when we talk about inner product. If you have a like xi 1, 2, 3, xj 4, 5, 6 as sample data, then the inner product will look like this. Some of the multiplication of all of those, that becomes 32 here. So the values that you apply on this kernel is simply, if you apply this kernel on xi and xj, xi is current, x in current dimension, xj is the next dimension, then the values that you have, then you calculate some value as kernel over there, very simply. Nothing very complex over there. And I've written some point for you, that is dimensions. So on the other hand, we can have polynomial kernel. In polynomial kernel, we want to bring these calculations to the power of d. That this is the dimension. What I showed you as x to the power of 2, x to the power of 3 in linear one. That we did this x to the power of 3 in first example that we had, very similar to that one, but of course we need to add some hyperparameters also to q, not only that d. So these hyperparameters includes the gamma. Gamma is constant that scales this dot product. This dot product can be scaled based on gamma. Also, we have the R, that is also a constant that also we added to this scale to adjust the scale that we have based on the R. And D again is another hyperparameter that shows the degree of the kernel that we have. For example, in that example, we choose an x2 to represent x to the power of 2. So most of the machine learning techniques, the algorithm that we have, we need to adjust some hyperparameters. So how we can define hyperparameters? You have data set, you apply the technique with different parameters, you put some values over there by experience that you have, by other people's experience, then you run it, you see the result. Then you change the parameters, fine-tune the parameters to get better result, better final accuracy, better cross-validation value. Or you write some code automatically change the hyperparameters to find the best cross-validation value. So these are the hyperparameters that you need to specify, you need to adjust in the kernel that we have. So polynomial kernel, linear kernel. With the polynomial kernel, we compute the similarity between two data points actually, and we raise it to the specific polynomial degree that states this equation over there. We have two more famous ones: radial bias function, RBF kernel. In RBF kernel, pretty similar job. We just get the exponential of the some term over here. That here gamma is to control the spread of function here, not like if you have the Gaussian model, the spread of the, for example, Gaussian function over there. That comes from the Euclidean distance between xi and xj. The differences times some controlling the spread to the power of the exponential. It is called as a radial bias function, very popular in support vector machine. And what does it do? It computes the similarity between two data again based on the Euclidean distance. This Euclidean distance over there, that comes to the power of exponential. Or it's like, because it's to the power of exponential, it's based on the normal distribution or Gaussian distribution also. On the other hand, the fourth one is the sigmoid kernel. With sigmoid kernel, we can write kernel of xi and xj is equal to tangent hyperbolic of this term over here. Again, we have two hyperparameters, gamma that scales the dot products, and the R. Then again, adjust the this scale again. So we need to put some value with tangent hyperbolic, then we can calculate the kernel. So what does these kernels are doing? These kernels are mapping our data to higher dimension to make it more visible, to split it with line, in support vector machine, simply. Again, if you want to define this term over here, we say sigmoid kernel computes the similarity between the data points using the hyperbolic tangent function. So now, as I mentioned, those kernels we have, the objective we have, now we need to put all together. In order to put all together, of course, we will have a little bit super big equation. The point is that before getting to that point, we say the kernel function, of course, is not loss function. The kernel function method transforming input data into the higher dimension. So we need to rewrite the equation as I explained, and we use in conjunction of the kernel with, for example, hinge loss that we defined. That was hinge loss. We can have another losses too, but I told you that this hinge loss is very common to use. Because of that, I'm also defining hinge loss in conjunction with the kernel that we can use in SVM. So if we consider we want to write hinge loss function as a nonlinear with soft margin SVM, because we said we have maximum or soft margin, we can write the equation like this. What it is? Actually, we have the kernel over here that we defined. The same kernel that we defined will be replaced over here. The right side we already explained. The left side is coming from one new parameter. Alpha is coming from Lagrange multipliers. Lagrange multipliers comes from mathematical definitions that in SVM shows the importance or weight of each training example or coefficients of the support vectors. So we can say, okay, the importance of each training example. So how important is this? How important is this? How important is this? Comes from Lagrange multiplier that we need to add parameter alpha over there too. So I also stated one more point, that in mathematical optimization, we can use it as a strategy to find local maxima and minima based on some constraints. So local maxima and minima means that if you have a curve, you want to find higher or lower point over there. In mathematical, it is common to use. So if you're interested in, you can study it more, how that's working and how this is coming out. I don't want to prove it exactly how the calculations can be applied to finally achieve this. But what is important for us to know, first of all, the kernel that we defined, we want to plug it here. The loss function, the hinge loss function that we've had over there. Just the point is here, we need to change hinge function a little bit and replace it with f of x here. Why? Because now we want to calculate it based on the predicted label. So the y is the real label. The f of xi means that I have the support vector machine hyperplane. Then I will do some prediction, and based on this data, the predicted data and the true data, I want to calculate the hinge function. Just replacement, a little bit change over there. So of course, this alpha I, and alpha j comes from Lagrange multiplier, and yj is the true label of the data in dimension, first dimension and next dimension. So if we have a look now at the term, we know all the parts. Nothing is missing, and C already we defined that how big should be the margin over there. Should be clear. Now, how to implement it? All that efforts that we've done today, if you use library, comes to these few lines, simply. So that's why I'm not letting you to use libraries, because all the course that is studied today, I can show you here. Now, look, from scikit-learn, I import SVM, then I write classifier is equal to SVM.SVC, because I want to use classifier, SVM.SVC classifier. Kernel, I define the kernel, linear here. But what else I can define as kernel? We studied today. Polynomial, RBF, radial bias, sigmoid, or if you have pre-computed, you can put it there. So in library, whole options that you can replace it with linear are these, and we studied all for SVM. You can replace it with kernel. What was the C? The margin. I said that, you can put some value. You can even in library, don't write it. If you don't write it, C is equal to by default 1. Or when you want it, you can change it to increase and decrease the margin. So in one line, you define classifier, whole classifier, then you write classifier.fit. Input data and labels. Finished. Whole equations, whole mass, whole the things that we studied, 2 lines finished. Then what we need, if we have linear classifier, we need the intercept and the slope, right? To know what's the line, where is it. You just say classifier that coefficients is W and classifier that intercept is beta, is the bias. So W and B, and you can plot it now. It's a line. This shows the slope. This shows where up high is. You can plot it, and that's it. You have support vector machine with the data set that you have. You can apply it. But as machine learning students, we want to develop new algorithms. We want to understand the underlying concepts. We want to be different from people who are using these algorithms as black box, and they just don't know what, like, now clearly you know what does mean the kernel. Now you clearly know what's the C. You can clearly adjust it because you know the background exactly. You know what is it doing, how many it's allowing. So this is the whole idea that we are diving in. Okay. Now let's look, if we discussed about classification. What if we want to use SVM for regression? What we should do? We say very similar to classification problem. We do hold the steps same. In regression, instead of distance between the hyperplane and training examples, we use the same margin to measure the deviation from predicted and actual value. So instead of using the distance of, because we were like using the distance of these and see how to push them to the margin to the edge. But here instead we can say let's use it for prediction of the actual value and predicted value. That's it. Then what we need to do, we need to modify the objective function to minimize this prediction, to minimize distance between predicting and actual value. We run everything same, we just change the objective function from classification to regression. What are the advantages of using support vector machines? We say support vector machine is popular, flexible machine learning algorithm that can be efficiently used in wide range of applications. SVM is working very effective in high dimensional space. If you have like 100 dimensions, SVM can work perfectly good. SVM is robust against overfitting because of that parameter C that we have. SVM using the kernel function that usually work very well with nonlinear separatable data. And the point is that instead of splitting, for example, in this kernel, in linear kernel, in splitting data like with some curve, with some nonlinear function, we add dimension and still we use simple line to split data. And that was like kind of very nice idea that makes SVM very good algorithm. SVM still works well when number of features is greater than number of samples. In some problems, your feature space is bigger than samples that you have. Your data is less and you have lots of features. SVM works pretty well there. And still we have less hyperparameters to tune compared to other machine learning techniques. Although I introduced some in kernel and parameter C, but it still is lower to fine-tune it. So let me bring all. So we say, okay, if we want to, although we haven't studied deep learning, but you've heard or you are familiar with a little bit, let's have a general look what is the advantage of the deep learning SVM over deep learning techniques. SVM is data efficient. SVM is faster for train, especially with medium-sized data sets. It is more robust to noisy data. Deep learning is more sensitive to that, unless you have very big data set. Transparency and interpretability. Here, transparency is very high. As I mentioned in first lesson, that when you have black box model machine learning, that's a little bit scary at some point also there was some interview from machine learning guys with TV show that the interviewer asked, okay, you know how the decision is happening in the model that you have. The answer is we know, but generally, not exactly what is happening, right? And if it becomes very complicated, like brain of human, then we have no idea what is happening. We know underlying concept. We know how the weights are calculated, but we don't know what is happening exactly to make different decisions. Then the neurons can learn something that we are not expected to. Then that will be a little bit dangerous. We should be careful about that. That's the issue that also challenge that in future we should consider, but here we don't have that problem because we have transparency. It can be scaled up to large and mid-sized data sets. On the other hand, but you may say, okay, then SVM is good to use always. Not really. It is strong. We still, I told you, still in many research, we use SVM as very popular technique. But on the other hand, deep learning has some advantage, like ability to learn complex representations. If the data, the correlations and everything is very complex, deep learning can work better, and it can handle unstructured data sets better. And if you want to say that which one to choose, the choose is between the depends on between the problem that you have and the data set that you have. If you have low amount of data set, SVM even maybe work better than or equally same as the deep learning models. So what are the applications? For example, in only one image processing, if I want to state for SVM, you can use it for object detection. You can use it for image segmentation. You can use it for face recognition. You can use it for image classification. You can use it for medical image analysis. So all these concepts that we use can be applied on these problems over there. We can say, okay, if you want to kind of conclude what's the SVM, SVM generally can be good in situations where data is high dimensional or number of training samples is small. For example, you have 100 images and you want to do classification. Then it's better to not train deep learning model. Use SVM can still work for you. What are the challenges that we have on the other hand? We need to be careful with the kernel function selection. The hyperparameters tuning, the parameter C can be a little bit challenging to fine tune. Difficulty with very big data sets. If your data set is too big, then SVM gets into the problem. And the parameters, the parameters can significantly affect the performance that we have, the hyperparameters. So based on our discussions today, now I will show you whole implementation all together with the codes that we have. And based on that, you will have a practice for today that you need to implement k-fold cross-validation to determine C with the given example. So you need to apply cross-validation and determine which C is the best for the example that I'm going to give to you. Then you will have an assignment for next week. You need to use support vector machine to solve previous chapters spam detection example that you've had. You still can use the library. I allow you to use library in this case, but you need to do evaluation and cross-validation perfectly fine over there. Optional, instead of that, if you are interested in, you can SVM to solve one of the desired image processing applications. You can take a data set, a small data set from internet, and try to apply support vector machine to solve that problem. So that you can see how it is working and you can solve a real application much more with a more realistic data set. So today what we discussed, we understood the concept of the SVM and how we can apply stochastic gradient descent, why we need to apply stochastic gradient descent on it. We learned how support vector classifier is working. We discussed the hinge loss and how to use it. We defined the kernel function to use in SVM, and we understood kernel trick and how using kernel trick with explicitly transforming the data with only equation. Not doing that, we can solve SVM problem, and that was all that we today understood.